So welcome to this 3-day intensive PhDOpen course. The topics that we will try to cover throughout these 3 days, there will be 3 parts. Today I'll try to introduce the kinds of theorem proving systems we will cover in the course, and we'll already see some of the problems that can be handled by machine learning. So it comes out that automated reasoning, the automated deduction, has been a field of AI, but it split off from AI already a few decades ago, and the techniques developed there would be more on the heuristics side. These heuristics are very powerful, but they are quite far from how humans do reasoning, from how humans approach mathematics. That's why I'll introduce some of the machine learning problems that arise when doing computer mathematics. So we'll look at problems such as the selection of lemmas from a large database, such as the transformation of informal mathematics to formal ones, and well, I'll introduce the various problems and say how do they relate to problems in machine learning. Then we'll start today with one of these, namely the lemma relevance problem. If we have a large library of formal mathematics, and today our libraries are measured in hundreds of thousands of facts, selecting some of these that are relevant for a given problem ends up being an interesting issue. And I start with this problem because this is the one where actually machine learning techniques have already been the most successful thing we know, whereas for the other domains we're still struggling to beat the heuristics developed over the past few decades. And so as part of the exercise session today, we'll look a bit more on how we can define features, that is, how to characterize mathematical reasoning, what is important there, and we'll also look at deep learning approaches, so somehow the opposite of the features. So that's the plan for today. Tomorrow we'll look at core ATP reasoning calculi, so we'll look at the various logics where procedures have been defined, and we'll see what is the state of art. Resolution is the basic method for dealing with first order logic. We'll be focusing quite a bit on first order logic, but I'll also say something about the weaker problems, so how to go from propositional logic, from SAT, so somehow the simplest NP-complete problem, to problems that are already semi-decidable, what lies in between. In fact, there are some people working in this faculty on description logics and so on, which are in between, and then this extends further to actual undecidable calculi. Reasoning in resolution, that's pretty old, that's the 60s, but then the most basic methods, but then what the actual state-of-art provers do, they would combine resolution with orderings, and orderings at 2 different levels, being able to eliminate various derived intermediate clauses just because they do not satisfy some order on literals, some order on variables. That optimizes the resolution calculus quite significantly, so I'll say something about how this is done. And the second part is equality. Equality is very common in both mathematics as done by humans and in computer problems, in problems about actual programs or hardware, and therefore automated reasoning with equality has been a major focus of automated reasoning, and we'll see how we can learn things about reasoning. So there's lots of optimizations and heuristics, and I'll try to show how much of this can be learned by modern learning methods, what has been tried. So both when it comes to what are the foundational steps, what are various tactics and procedures, what can we learn about the orderings, and so on. So that's the plan for today. For tomorrow. and tomorrow will be a bit more theoretical. So today the plan is this is going to be more on the practical side. We'll see what actually works, how it is connected. Tomorrow there will be quite a lot of theorems, but since it's a short intensive course, I'll not give any proofs, just let you trust this and give you pointers on where to find the actual properties of the various calculus. And the last part 3, on Saturday, I'll say something about the actual open problems and things where we are hoping to beat the state of art very soon. So I'll say something about individual reasoning steps, about selection of strategies, and finally, automating formalization. I'll give a hint about this last point already. Typically, if we think about mathematics, if we think about computer programs, we are thinking about sentences in natural language or some subset of natural language such that another human can read it and can understand it, can follow the proof. This kind of proof is not understandable for a computer. For a computer, a statement has to be a statement with a particular syntax for which semantics is defined. So we would normally focus on a logic, be it first order logic, higher order logic, or even something more complex. It's still a restriction of what can be expressed by natural language. Therefore, we are considering this process of formalization where we're going from the informal text to fully formal text, to a text in a language where both the statements are understood and the proofs are understood by a computer, where the computer can actually check the proofs, and I'll say something about this already today. So that's the rough outline of the course. Let's head on with the first part. Automated reasoning becomes an interesting challenge for modern AI methods. We've seen AI being able to beat a lot of games. Some time ago it was games such as chess or today games like Go, or even, well, I guess you are hearing all these results from other courses, so I will not repeat them. And there's this feeling that every couple of months there's a new paper that we have been able to beat another game, a game where another kind of move is necessary, where this is real time, where you also need to recognize the screen and so on. So there's a feeling that if we put another couple of months, half a year or a year into the next game, we're going to be able to beat another game and another game. But games are things that humans learn rather quickly. Typically, a human is given the rules of the game or just given an interface, and in a short time they can learn this. This is not the case for mathematics in the sense that if I am given a statement to prove, well, I'm going to struggle with it for ages. I'm going to struggle verifying if these are actually valid proofs. Even if I'm thinking about some quite limited logic, first order logic, this is going to take a very long amount of time to figure out how I can prove something, and to reach the point of actual mathematicians that prove theorems today. Well, I cannot do this, so that's somehow beyond the skills of every human. And this is not only the case for us, but it's also the case for some of the professional mathematicians. Already back in the 90s, we had the so-called Robin's conjecture. This is a theorem with a statement that can be expressed in one line. Well, I'm not going to read this, but it's a one-liner given an associative operator plus the following statement holds. This statement has been attempted by a number of human mathematicians. It's been an open problem for many years. People tried it, people have failed, until an automated reasoning system would be fed this sentence and then run for a week, I forgot if it was a week or a month, and would say, I proved it. Okay, well, there are multiple issues there. One thing is, did it really prove it? And yes, this has been verified that the system is sufficiently small, the output of the proof is sufficiently small that it can do it. Second thing is, if it managed to prove it, if it did something that a human cannot do, how did you do that? I mean, what is the special technique that was used there? And the technique used for that proof would be essentially this resolution with ordering, with equality handling, which I will explain in more details tomorrow. So we'll know how it does it, but then even if it knows how to deal with it, even if it can find a proof, the proof is a few 100,000 steps. So what is the meaning of this proof? How can we get back from such a proof to a proof that a human understands? And that's actually one AI problem already here. Which are the important steps in a proof? We'll come back to these problems. And the second thing is, can we extract some important components here? So this idea, the idea that a computer program would prove a theorem that has not been proved before is something interesting and exciting, and there are fields where this is actually happening. So Professor Kini and Professor Verov are working in the fields of quasi-group theory and loop theory, where currently what humans can do is weaker than what computers can do. These are like two very small fields of mathematics. Well, it's like 1% of mathematics, but this is happening, but there's a particular field where humans can do less than what computers can do. And here we need to figure out what is the meaning of these proofs, extract interesting lemmas, extract interesting new concepts, or even think about what else it is that we normally do as mathematicians, whether we propose some new interesting conjectures, whether we try to figure out some analogies and so on. Can the computer do? So this is really small, but there's a much bigger part. There would be computer-assisted proofs, where rather than doing the complete thing, a computer would help fill the gaps or deal with some corner cases and so on, and I'll say more about this later on. So that's one issue. Some higher math is too hard for mathematicians. That's why we need more automated reasoning, and we need AI to make this reasoning strong. The second thing is proving properties of computer programs. Computer programs are becoming major, and failures in computer programs are costing us lots of problems. Therefore, we're starting to consider showing formally that a computer program is correct. So, well, I don't think I need to convince anyone here that testing is not enough. Well, you test for 1 million inputs, it works. For 1 million first, it doesn't. But if you prove it by induction that for everyone, that every possible input is fine, then you're done with it. And there are more and more programs proved in this way. I'll introduce a description of automated reasoning. So what I mean by automated reasoning is the use of a computer to perform reasoning according to the inference rules, according to the allowed steps and syntax of a particular foundational logic. And this logic could be propositional logic, where we know how to build formulae, where we know what are the basic possible inference rules in propositional logic, but then you can continue extending it to more complex calculi. Well, propositional logic is too limited to reason about programs. You want something stronger. You want to be able to do first order logic. That's still not enough to express higher order properties, such as termination of a program. That's typically the typical way to express it would not be first order. It's traditionally a part of artificial intelligence, but not machine learning, and the field has been there since the 50s. I've already said something about the applications and the logics vary quite a lot. We can extend first-order logic by features such as higher order to reason about things like complexity, but also we may be interested in things such as dependent types, or even going into the languages such as the calculus of constructions. Is calculus of constructions and calc known to people here? Can I have hands up? Okay, about 1/4. All right, so I will not be going too much into the foundations throughout this course. I'll rather stick to the calculi where automated reasoning can be done efficiently, but if you want to express very complex properties of programs, such as a sorting program is a program that given a list returns a sorted one, these would be very concisely expressed in more powerful languages. I've here copied a slide from Ms. Broda about the spread of theorem proving that gives some ideas of the fields that exist. I will keep it as a background for me talking about it. So we have traditionally propositional logic where we are only talking about atoms and we're talking about propositions connected with just the basic, in minimal logic there would be just a set of two connectives, then we increase this set of connectives to get full propositional logic. We extend it further to either first order, but there's the other direction where we can look at non-classical logics, so logics that are intuitionistic, or even logics that would include some properties of models. So we could be talking about temporal logic, about linear logic. We're extending this environment. So linear logic where we can use a proposition a single time, a fixed number of times, and so on. The other direction how theorem proving evolved would be in the direction of logic programming and Prolog, and the foundations of Prolog would often consider either answer set programming or things like IOP, which are today used for reasoning about term rewriting and complexity of term rewriting. The other direction would be common sense reasoning. We have large libraries of people trying to describe the world in some logical way, where we are trying to describe properties such as, well, Warsaw is the capital of Poland, London is the capital of Great Britain, and so on, and then trying to reason about them, that every country has to have a capital or not. So where you can do not only deductive reasoning, but also inductive reasoning, where you can try to conjecture properties and try to disprove them in the logics. Reasoning with equality would be much more common for now. I leave this as is and continue. So one of the basic tools that we'll talk about would be Proof Assistant, and I'll here introduce it as a black box. So I have here the traditional definition following Professor Hager's. A proof assistant is a computer program that assists a mathematician in the production of a proof that is mechanically checked. I've split it into bullets so we can try to understand it. Well, it is a computer program, so it's something that can be implemented. So it's an implementation of a logical system that assists a mathematician. Well, here I call us mathematicians, even if I imagine half of you are computer scientists, in the production of a proof. And again, what does it mean that we are producing a proof? That means we are producing a text that is encoded in a computer, so in a computer understandable language that can be mechanically checked. The computer can actually verify that it follows the rules of the logic. What does it do? Well, you're typically setting up some theory. Let's say I'm going to reason about an operating system, so the operating system is implemented in some formal language. I specify the language, the semantics of the instructions, and so on, and I define the functions that I have there. I make some assumptions. what is happening and try to show properties of that operating system. I'll give an example of this in a moment, and it typically allows proof editing, proof checking, and hopefully it can do some automation that is proof switch. Why is it hopefully? Traditionally this is not necessary, but if you do not have that component, you cannot do anything major. You're going to only build some very simple toy examples, but with automation you can build major proofs about actual computer systems. So what does it implement? It implements a formal logical system intended as a foundation for mathematics, and first-order logic could be enough, but it's often too restricted. We're typically going to consider something a little bit stronger. Still, when it comes to automated reasoning, the automated reasoning component, first-order logic is often enough. It also implements a number of decision procedures. If you are reasoning about a program in something like Hoare logic, you want to be able to decompose programs and combine such Hoare triples in some intelligent way so that you can more efficiently deal with them, and that is not general automation but rather particular decision procedures for restricted fields. In particular, if you are looking at something where you're reasoning about the memory, and the memory you encoded as potentially distinct integers, you want the decision procedures for integers so that it can discharge a big number of goals that arise. And use of proof assistants. 1611, Johannes Kepler stated the Kepler Conjecture that said the most compact way of stacking balls of the same size in space is a pyramid. And here this is maybe a small one, but you can imagine how it grows. This is the most compact way of packing balls. If you rearrange them somehow, you're not going to get something better. This is the volume of the pack. Very nice. The conjecture stayed open for almost 400 years until Tom Hales claimed that he found a proof. What was this proof? The proof was a 300-page text accompanied by 3 computer programs. Okay, nice. So the proof was submitted to the Annals of Mathematics. A big group of referees looked at the proof for a number of years, and finally they said, well, we've looked at it for the last 5 years of our lives, and we're almost sure that it's correct. It's only 99% correct. We cannot verify the program. They looked at the 400 pages, the 100 pages. Well, that looks okay, but we cannot verify the programs. What are these programs? Well, one of the programs would be Mathematica, which is like, you can imagine how big computer algebra system is, and that would say the following inequality holds. Sounds like an inequality that one could try to prove, spending a month of their life to prove one of these, and there will be 1,000 of such equalities and inequalities, and 2 more programs, one enumerating graphs that have a certain property, and so on. So this is an example of a modern proof. There are not that many proofs of this size, but the forums about higher mathematics would have a number of proofs where, well, this is such a long text and there's a lot of assumptions from other fields that we are not absolutely sure if this is correct. So what's happening here is Tom Hales decided to start a project to formalize or the logic. But as part of the proof, we had to encode the 300 pages in the proof assistant, and as actually in the proof assistant, the work required to do that would be more like 700 pages. There would be 20 people working for a couple of years to deal with the issue. So that's one example. And I've already mentioned there would be 20, so something between 20 or 30 person years required to complete such a project, which means it's a major effort. It's more than what the referees put into the particular verification. So, well, we're kind of swapping one thing for the other. Is this a solution to the problem? So far, no, but the thing is, we are using a proof assistant which can do automated reasoning. And if its automated reasoning capability becomes stronger, we can get rid of that factor. We can make it more efficient than traditional mathematical refereeing. And also, this is verifying properties of the programs, showing that the code is correct, can be more efficient than human refereeing of code, which is very exciting. Second example would be, for some of you, it may be around the time you were children. Certainly was for me, the Intel Pentium bug, 1994. Intel has published its new processor, and soon after that, a person discovered that a certain division result would be off. The issue has been quickly attributed to the division lookup table error, but, well, what happens then? You either have to not trust the division operation of the processor, which is pretty horrible. You have to recompile every program, or actually what some of the systems would do would be drop some instructions and make the whole thing run slower because you have to possibly fix the results, or exchange the processors, and Intel decided to offer the replacement of all its processors, and that was $500 million. And since then they employed John Harrison to try to certify their processors correct. That was the birth of one of the proof assistants, and also since then significant parts of Intel and AMD hardware is formally verified. What I mean by significant parts of would be all the arithmetic operations, and including all the exponential and sine functions, which are now included as parts of the extended processor instructions. So this was a paper still in the 90s, 2006, I think, was a paper which extended that to the 64-bit architectures, and a few things happened after that. So yes, this is not, formal verification is not the only part. There's a lot of model checking and so on used for verifying processors, but when it comes to the harder parts, such as making sure that some optimized division that looks up a table and then looks up the difference and specify this corresponds to the IEEE specification of the floating point numbers, that's a major mathematical proof which can be formalized and verified. How do these correspond to other kinds of tools? The actual automated theorem proving systems, which we'll focus on more tomorrow, would be tools that essentially do automation only. They focus on the automation rather than a powerful specification language. Systems there would include Vampire, Improver, or Spaß. These would be the three major ones, but I'll say more about these tomorrow. And they are being used for proofs such as the Robbins conjecture, the inner mappings project, but also a number of properties of programs would be translated to automated reasoning techniques. And this is quite different from what model checkers do. There's no proof there. The proof would be completely outside of the system. or computer algebra, which performs mathematics and helps it, but does not actually do proofs again. Okay, so maybe this is, I hope, my last slide that introduces interactive theorem provers before we'll head on to where is the issue with them and how learning can help. So theories and programs that use interactive theorem proving, I've already said something about Kepler Conjecture, and there are two similar kinds of proofs. The proof of the four-color theorem has been performed in the co-proof assistant, and the Fate-Thompson theorem, or the classification of all the order groups, is another major project. And the same thing is happening with software, processors and chips. I've already said something. There will be a number of hardware cryptographic chips that are verified in this way, but also we have security protocols. We have a certified compiler, actually not just one today, so in 2009 the first certified compiler has been created. That means a compiler that transforms C code into assembly, performing the same kind of optimizations that something like GCC does, but at the same time it certifies that every single optimization that is performed preserves the semantics. So we have a compiler that preserves the semantics of the original C code to the output assembly. It would have something like 14 different intermediate stages, intermediate representations, where you're doing subsequent refinements, with some of the steps being very simple, such as elimination of dead code, or loop unrolling, but some of the optimizations would be pretty hard, and bugs that arise in these stages are pretty hard to detect and eliminate. Now we have more of these. We have projects that are compilers as good as GCC, but they also preserve complexity and are working well with parallel code. L4 Verified is an operating system kernel. So L4 is an operating system kernel. L4 Verified is a project that tried to verify an operating system kernel, but they specified a number of properties that you want to have preserved, such as the fact that a program cannot peek into the memory of another program. So similarly, a program cannot peek into the memory of the kernel. So in this way, by showing that such a property is preserved by the implementation, you are hopefully having an operating system where a kernel oops is impossible. Of course, well, the system is a minimum system. Well, it used to be a minimal one. More and more parts have been verified, including the file system code, the scheduler, the memory management I've already mentioned. So they're working on this project, and this is software you can install and run on your computer that is going to be more certified than usual. But there are a number of issues with proof assistance. The first major issue would be the fact that the libraries of systems are quite limited. So if you are trying to start a new formalization project, you will likely need to specify parts that are missing. Typically, something like natural numbers, integers, or real numbers, this would already be there, but as soon as you're reasoning about a more complex data structure, a more complex mathematical term, this would require some additional work. The automation, that is a major part of what we will discuss in these 3 days. The automation that is provided is pretty limited in comparison with what a human considers obvious. This has been quite an important field of research, this obviousness to a mathematician. What does it mean that a given sequence of reasoning steps, or a given sequence of mathematical statements, that this is obvious? What does it mean when it comes to an implementation? How can we realize that? and there's a lot of different automation techniques. Today, some of them would be, as I mentioned before, surprisingly stronger than humans. In very few fields and very little domains, we are getting to places where such a system can surprise you. It can say, I've figured it out, I've combined these 30 facts from the library somehow magically, and so it's now obvious, and one of these facts says like every natural number is even or odd, so you know like the proof should now follow by cases, and you do different things in the two cases. There are such cases where the automation is stronger than what a human does, but they're pretty rare. Most often we're still behind, and we're trying to employ some learning techniques that are going to help us figure it out. This is the third one. The third major problem is the communication. If I communicate with a high school student, I tell them about a certain procedure. I tell them, well, the way to normalize the polynomial is as follows. We put this after that. We're doing some actions. Whereas, in a typical proof assistant, whenever you're introducing a new procedure, you have two options. You either do it again and again yourself, or you implement the procedure. But there's nothing in between. There's nothing where you are the one giving some intuition and hoping that the system can learn to proceed according to that intuition. And that's what we would really like. We would really like to show an algorithm by just a few examples. We're normalizing polynomial 1, 2, 3, and, well, a high school student will learn this. A PhD student will figure it out by themselves without being even shown. So, but like a computer system has issues with basic communication and does not learn even simplest things that we try. Here come the main AI problems that arise in theorem proving, and I will divide them into three classes. So I'll divide it into the so-called high-level problems, middle-level problems, and low-level guidance problems, where by high-level I mean actions where we are calling a machine learning procedure every long amount of time, where we are looking for something big. Whereas on the other end of the spectrum, by low-level guidance, I mean trying to decide on every inference step. So here, we typically would have something like 10 seconds to make the decision. What is it that we want to do? Some proposal how we're going to attack a goal. Whereas here, typically, these inferences happen hundreds of times per second, maybe even thousands of times per second. So a classification algorithm, a regression algorithm, has to be comparably efficient. When it comes to the high-level AI guidance, the first problem, and that's going to be essentially the rest of the lecture today, will be lemma selection. Mathematical libraries contain thousands of books, but when it comes to the parts of the knowledge that is computer understandable, that is typically in the range of hundreds of thousands of facts. And I'm saying a range of because we're talking about different logics. So we have a similar amount of knowledge in first order logic, but we also have this amount of facts in higher order logic. We have this amount of facts in propositional logic. They concern sometimes different domains, but possibly with some overlap. Some of them include proofs, some of them would just be encodings of an intuition. So we have these libraries, and whenever we're trying to do a subsequent proof, you may want to try to decide which part of the library would be relevant for my current proof. So I'm now going to do a proof. This proof talks about a topological space. As a human, if I go to a library, I'll know that I will need to look at my 5 books on topology, but books on domains that are completely different, I can ignore them. I most likely do not need complex analysis for my topology problem. There's a chance I could, but it's very unlikely. So I'm going to be able to somehow order my knowledge. First, order it in terms of books, and then order the actual knowledge that is there in a way that the more relevant one comes first. This problem, the problem of lemma selection, is also a major one for theorem proving, both when it comes to interactive theorem proving, where we are trying to prove a property of an operating system, and therefore we need to look at our library of 100,000 facts. If we apply an automated reasoning procedure, it's typically going to explode, so we want to restrict our knowledge to parts that are going to be relevant, somehow use only the facts that are relevant for the particular goal. That's also true for automated reasoning. When we have a single problem in first-order logic, we also want to perform a similar kind of restriction. The way this is done would be we are looking at features of the logical statements. How is it that as a human, I look at a statement and I have the intuition, this is about topology, this is about analysis, it talks about openness. We have some ways to characterize logic. And this would be a second AI problem, how to characterize logic meaningfully. I'll give an intuition of this, we'll come back to that later on today. Typically, if you have a statement, it is just a sequence of, let's say, symbols, then we can try to apply various machine learning techniques to characterize that sequence. Let's say I'm going to use some n-grams or something like that. If I now take my logical statement and change one single character, namely add a negation in front of it, the meaning of the statement changes completely, but the majority of all kinds of syntactic features stay the same. So you need to be very careful when characterizing statements, and such syntactic characterizations are useful, but they're missing a major point. How can we characterize logical statements meaningfully? Then how we can learn from related proofs. For this, we first need an encoding of the proofs in a computer understandable way, but also a way to extract relevant information from the proofs. A similar AI, high-level AI technique would be the selection of tactics. What is it that I want to do in general? Something like I want to approach this by induction because similar goals required induction as the major technique. This induction is maybe a very specific tactic. In some cases, I will do it by something like completion, by rewriting, by resolution, and so on. What is it that I want to do? And again, this would be a thing where I have quite some time to think about it. For mid-level guidance, the kinds of problems that arise would be selecting strategies. A typical ATP, a typical automated theorem prover would be pretty strong as a whole, but actually the way it runs is it runs various strategies for some short amounts of time. Each of these strategies would be maybe 2-3 times weaker than the combination. This is the thing that happened in various domains, and when it comes to automated reasoning, this happened because of the competitions. People figured out that a combination of strategies which are very complementary, run for short amounts of time, where you throw away most of the derived information, is going to be significantly stronger than even a few of the best ones. Therefore, we may be interested in selecting the particular strategy for a given problem. Second thing would be learning lemma and concept reuse. If we have our library of proofs, as part of the library, we're typically deriving lots of smaller statements, lots of smaller sentences. Which of them are going to be reusable, useful in other proofs? That's again pretty interesting to look at it and select them and cache them. there would be very simple things that you can figure out here if you use some trivial technique. Looking at the proofs, you realize every time I'm dividing an equation by 2, I have to show that 2 is different from 0. So maybe caching the proof that 2 is different from 0 is a useful thing. This is completely unuseful for a mathematician, but actually, if you think about it, it's something that you have in your head. It's maybe you have it partially unconsciously, but you have a number of such simple properties. There would be a number of more major ones that appear in proofs that are reused and that are likely useful again. And conjecturing, I'll talk about this more on the next slide. But in general, as a mathematician, I'm proposing some intermediate goal. I'm proposing some extension of the library. How far can this go on the level of AI techniques? And finally, guiding every single inference step. That's going to be a major focus of tomorrow. What can we do about it? How can we make a procedure that is at the same time efficient enough that it doesn't slow down the system, but at the same time that it's useful, that it's more useful than just doing brute force search. Okay, so given this division of the problems from the, let's call it, performance side, let's look at it the other way around. What are the problems from the theorem proving side? What would be interesting? And the first problem would be, is a statement useful? So we're typically, in an automated reasoning technique, we are deriving more and more new intermediate statements. We combine something that we know with some other thing that we know. We have a new fact. We're deriving lots of these possible facts. There will be thousands of them. There will be millions of them. So maybe using them again and again doesn't make sense. Maybe some of them are more useful than others, and being able to characterize a statement as a useful one or not would be a very interesting learning problem. And this comes in two flavors, an unconditional one and conditional one. So we're trying to derive something that's useful for a conjecture, that is useful for a goal that we're trying to reach, but also in the unconditional setting where this may be just unuseful because it looks like a tautology. We've derived something that looks complex. It talks about our topological spaces, but in the end it's like A or not A, so there's nothing exciting about it. So these two problems will be somehow related, and I'll already say something about these conditional and unconditional problems. The conditional ones would typically be considered harder when it comes to the machine learning side because you have to make it dependent on something. On the other hand, when it comes to the usual automated reasoning heuristics, the heuristics are by default the conditional ones. Therefore, this will be the more natural thing that is in many systems already. The second problem would be, what are the dependencies of a statement? So premise selection or lemma selection. That's what I discussed a moment ago. We have a lot of statements in our library. We want to decide which of them are the ones useful for a particular goal. The next one, is a statement important? We are deriving lots of information, deciding whether this is useful to be saved, this is useful to be named. And sub-question, that is a fun question, but it actually ends up being pretty relevant. What name to give a statement? If you think, as a mathematician, I have a property of addition, so of addition for natural number, just the plus. The plus is a commutative operation. If you communicate with another human mathematician, you talk, well, the commutativity of plus being commutative, the symbol plus, the add, or so on. You change these names all the time, and the other person understands you. Whereas, for a formal system, a statement typically has a handle, has a way it's named, and having a good name, or the other way around, being able to recognize it by any possible name, is an interesting learning problem to have this correspondence between informal way of referring to mathematics and the actual statements. What should the next individual proof step be? What should the next tactic or instantiation be? These three are pretty related questions. We've talked about selecting individual inferences. Depending on the calculus, we either have an inference in the form of a calculus rule, or we have tactics in a system, or we're able to perform instantiations. For example, in the Nikanov system, the major thing one does would be to substitute general sentences by particular instances, and therefore selecting them simplifies the problem. Well, in further logic, you make it propositional by giving all the instances. In a system that's more complex, you can go from an undecidable automated reasoning problem to a decidable one, which is clearly an advantage. Now comes the conjecturing part. What new problem is likely to be true? Here we have a library of facts. We see certain shapes of statements. Well, I gave us an example a moment ago that some operator is associative or commutative. We are in a new field, we define a new operation, we know something about it, so maybe conjecturing, oh, this looks like it should be commutative or associative. It's something that the system can propose, and it can be done again in the unconditional setting, but also in a conditional setting where we have a conjecture and we're trying to go from the original axioms to a conjecture, proposing some intermediate statement, something that will be true based on the axioms, but will simplify the proof of the conjecture. Is a very hard conditional machine learning problem, but at the same time, this is what I claim is the most natural thing for a human. Why? A human typically performs some kind of divide and conquer. We're starting from what we know, we want to go where we want to get, and we're trying to conjecture, well, hopefully this would be a lemma that I will prove that will let me prove the conjecture. So dividing my thing into two parts. And if you're able to propose such an intermediate statement of a conjecture, then our proof search, and this proof search is typically some exponential procedure, well, we're dividing the n in the exponential by half, therefore our complexity goes down enormously. So I don't have to convince you that this is great, even if 1/10 of our intermediate generated conjectures are actually useful. That would already be an orders of magnitude better than any traditional automated reasoning technique. The final one that people have considered, but it's a little bit funny, is a statement true. So like, I give you the Fermat's last theorem just as a statement and tell me, is it true? Does a human mathematician have any intuition about it? Well, you can try to do some testing, you can try to do some guessing, maybe some people have been known to conjecture things and claim that they're true, being some horrible, huge integral equations, but I think most of us don't have such an intuition, and at the same time what typical machine learning techniques can do is they can realize techniques that correspond to a couple of seconds of human thought given the knowledge. Therefore, here we are pretty far, but there would be, this would be done for propositional logic, this would be done for properties such as polynomial normalization, trying to guess, are these the same polynomial, are these two propositional formulae equisatisfiable or equivalent, that can be done to an extent. Okay, so this is somehow an overview of the problems, and I guess 3 of these would be what I'll be able to say something about in the short course, and today we'll mostly focus on these dependencies of a statement and premise selection. So, premise selection was the intuition. Given a library of theorems, a set of theorems, you can think of these as mathematical facts that have been shown in a certain way, or facts about programs. I'll repeat this. So facts, what do I mean by facts about programs? This would be a fact that the insertion sort program actually sorts a list. So these kinds of facts. So some mathematical properties of objects that we can describe using formal mathematical language, but these would be both mathematical facts and computer science facts. So given such a set of facts, a set of theorems, and a conjecture, we want to find a minimal subset of that set such that it can be used to prove the conjecture. So that's the intuition. There's, of course, a few leads there, a little bit more formally, but that's, I'll say in a moment why it's not completely formal. We're trying to find an argmin T subset of the big T that is minimizing the size of our T such that this set T is enough to prove the conjecture, and if the conjecture is not provable, well then we just have to return something. So in this case, the empty set will be a valid answer. Why is this not fully formal? Because it has some implicit assumption on what is the meaning of the V dash here, what's the meaning of the probability relation here. There's an implicit assumption on a theorem proving system. What can be, and most of these theorem proving systems are some semi-decidable procedures or even worse. Therefore, we're going to use an ATP in practice, ATP with a fixed time limit. So, what is the minimal set such that, given that set, an ATP can prove the conjecture within 30 seconds? This relation is, again, not going to be complete in the sense that you have so many possible subsets that you cannot test them all, so we're trying to approximate this relation. But the intuition should be clear. We're trying to find a minimal subset, but we're only able to test 1,000 of them. And we can run the ATP for a longer time, hoping that the bigger set doesn't hurt too much. We can try to minimize them and so on. The point is, we want to learn this. We want to be able to predict what is relevant for the particular conjecture. In machine learning terminology, this can be considered a multi-label classification problem. So, given a set of samples, where the samples will be triples, we have a proved theorem S together with its features of S and the labels, where the labels would be what has been proved through the theorem. We're trying to learn the function that works in this way, that is given the feature is going to return after labels. So S is the sample ID. We are going to want these samples because they're a justification while we are looking at particular things. So that's part one, it's a justification. Second thing, a thing is also provable from itself, so you may want to consider that in derivation. F are the features, and we'll discuss features in a moment, but we can think of some very simple features. That is, the commutativity of addition, A plus B equals B plus A, can be characterized just by the symbols that appear there. Well, it has a plus, it has equality, it has some type of numbers. Very simple, very imprecise, but good enough to have an intuition about it. What are the labels? The labels would be what was necessary to prove the theorem, what was the minimal set of theorems used there, and here we're a little bit relaxing on the assumption that it's minimal. It's minimal in the sense nothing can be removed from this set, but hopefully there are many proofs of a given fact, and we may want to learn from multiple of these facts. So we're typically going to start with a human proof. There's a human proof of commutativity of addition that started with induction and natural numbers, and the three basic properties of addition. Given a library of 100,000 facts characterized in this way, try to find a function that, given a new set of features, is going to give us the labels, so what will be useful for that next fact. Are there some questions? You can ask the questions already. No. All right. It's not the usual.
Could you go back to the other side just a second?
Okay. I was too fast, so I'm going to explain it again. So we have a library of facts. The library of facts would be each fact is the name of a theorem, so just some ID of a sample. Here the ID would be the fact that addition is commutative. Then we have the features of the sample. So how do we characterize it? Let's say we characterize it just by the symbols that appear there, the plus equality and the type of natural numbers or whatever numbers. So let's say that here we're talks about commutativity of addition on numbers, and then the labels is how this was proved. We have such a library of facts. We want to learn from this library, so be able to extrapolate this function such that next time we get a conjecture, we are now going to get a theorem that talks about the minus equality plus numbers, reals, and whatever. It's going to tell us, well, to prove the theorem, you most likely need induction, but also you need a property of minus, you need some distributivity, you need some, and so on. Okay? Right. And the reason why we're including the sample and not just features and labels is what I just
this function we want to have, it's more like from a power set of features to power set of labels.
You're right. Yes. Yes. Function that, given some features, returns us. Well, what we want is typically going to be a number of the most relevant labels. Right? Why is it the case? The reason is we're going to use it as the input to the automated reasoning system. The automated reasoning system is going to explode and not do anything when it's given too much. At the same time, when it's given too little, you are most likely not going to be able to prove your theorem, so we are typically going to fix the end that we asked for. We're going to ask for 1,000 most useful facts. So in practice, we will ask for the n labels sorted by relevance, because we can also deal with them in the order that they're given for the given set of features. More? It's important that we understand the problem. So, labels correspond to premises, and samples corresponds to proved theorems, but the thing is, at the same time, a label, so our premise that we use, is very often a theorem. So, asked if I will use the board and chalk. I said no, but hopefully I will not be scolded for that. Okay, so we have let's say a theorem A and B that are used to prove the C, but then A together with the C are used to prove the D, and then D is used to prove the E. So what happens now? We have a proof of E from D, but in principle, since D was proved from A and C, we could think of it as, if we combine the two, it means we do have a proof of E from A and C. And we can expand it even further. That's part one, that this relation is transitive, and at the same time, the relation is reflexive, So it's not written anywhere among our assumptions so far, but of course A can be used to prove A in 0 steps, right? I mean, I just use it immediately for itself. So this information is not normally considered if you think about standard way to do multi-label classification. So you may want to adjust the algorithms to have it. By just unfolding the relation a couple of times, by including such reflexivity properties, hopefully it can learn enough, but at the same time, well, how important is such a reflexivity thing? Is it as important as a longer proof? Is a proof that is short the same as a proof that is long? So here, implicitly, this is a proof with an ATP that takes 1 millisecond, this one takes 5 seconds, so something relevant is going on there, so maybe we don't want to use it for major facts, we should rather include all of these together. So this is why it's not exactly the usual machine learning problem. Second thing, similar theorems are likely to be useful in the proof. So if you do not always want to learn it in the standard machine learning way that we have a proof of from A and B we derive the C, but also just the information that the features that theorem has and our conjecture is the same, suggests we are likely to want to need it. But they're also likely to have similar premises, so if we have the proof, we can go there, but maybe we don't have to. Maybe just by the reflexivity of the relation, we can find it. Theorems sharing logical features are similar, and theorems sharing rare features are very similar, so this is maybe closer to the text processing domains where things Pi, but it's even more than that. In order to define your real numbers, you have to have the property about the natural numbers that you're trying now to show. And so this is pretty important in the evaluation that we need to know about this. Right. So I already have my first test question, and I'll continue the lecture. But it's not yet time for the break, so I'll ask you this one. What machine learning techniques or tools would you think are suitable for premise selection? Something for everyone to think about. So, any ideas?
Maybe deep learning, because it's I don't know, very strong, and it's somehow similar how our brain works.
Okay.
I mean, I don't have an idea how you can get a network and use it for now, but I suppose that there are many of attempts to do it. So I think that probably deep learning is pretty popular.
So by deep learning, I guess you mean that you are not trying to characterize your statements, but rather hope that the network learns how to characterize the knowledge while building the classifier at the same time. And yes, that is a valid approach, and that will be covered closer to the end of the session today. A hint: deep learning is good, but it has a number of drawbacks. So it will come. So what simpler things would you try?
It looks like, I'm not sure if I understand correctly, but it looks like the feature size can be, so the feature dimensionality can be huge.
Yes.
So if you just throw like...
That will be on the, so this is one of the characteristics that I exactly wanted to hear.
Yeah, so probably you need to have something that is able to technically have features that have huge dimensionality.
Right.
I would imagine that if you just do a linear regression or something, then it would be hard, just implementation of that, because then you would have matrices that are size of your feature set times size of your feature set. So
Exactly. So that's one characteristic. The number of features, if we just characterize things by symbols or subterms, they would range in hundreds of millions of features. Their square matrices will be a problem, but well, so hopefully one thing that you could say is you can possibly reduce the feature size by some kind of decomposition, even random projections and so on. That's one way to deal with the problem. Other characteristics.
Maybe some clustering, as we look for something similar to our premises, or some similar examples.
Right, so clustering is definitely one thing that has been considered before any machine learning has been applied. So the non-learning methods that existed something like 10 years ago would look for similar statements existing in the library to our conjecture and do this often recursively. So we first look for like 5 nearest ones that include the features of these, and continue looking for 5 more, do this a number of times until we fill our buffer. So that has been used that has been discovered multiple times, both in the context of automated theorem proving, the so-called sign filter that is now a part of eProver and Vampire, so the two most efficient automated theorem provers does this kind of clustering, but also before machine learning has been considered, it would be a part of some interactive theorem provers. More characteristics. What do you think about the time that one has to update the classifier in comparison with the query time? If you are working on a mathematical library, how often are you changing something? Guess? Guess? I have at least 5 people who have worked with a system like POC. How often do you change something in your formalization?
Almost never.
Almost never. How often there's a new definition that is introduced? How often does your state include a new fact?
Like every time I want to put one.
Right? Which is? Every 5 minutes, your state includes a new fact.
Yes, but it's only cumulative.
It is cumulative in principle, however, whenever you get to a next sub-goal, some of the things disappear. Yes. So, we do have to have an efficient way to train our classifier. Sometimes the number of these new facts would not be that big. Sometimes we have 20 new facts and we want to be able to retrain our classifier to include them, to be able to predict them also efficiently. More characteristics.
Sure, but this looks like there are a lot of temporal kind of states that when you're doing a proof automatically or by hand, you just, now it's something more important than something else. But if you use the equations later, it can change.
It can change.
So you may need some techniques to just adjust to these changes while you're doing this automated reasoning.
Right. Right. So that's what I mean by efficient classifier update.
Yeah, but I also mean that not only kind of updating, but also a way to say that there was a sequence of steps and it will change during the time. So time.
Okay. Interesting. Good. More? Okay, I'll unfold my slide. Efficient learning and prediction. So frequent major data updates. Whenever a definition is changed, then a lot of proofs, including those done by automated reasoning, are going to change. Therefore, your training data changes and you have to retrain. And automation cannot wait more than 10 seconds, often less, because otherwise a user is going to start doing something else. Otherwise, the brute force procedure, calculus like resolution, is going to be able to do more than what you can do. Second thing, multi-label classifier output. The multi-label classifier is often asked for 1,000 or more most relevant lemmas, so you need to be able to do that, and most tools would be able, even if they're doing multi-label classification, they get the first one and then separately they try to get the second one and so on. So like it works for 10 but not for more, and asking it for 4,000 is going to kill the tool. Second thing, it's easy to get many interesting features. We'll discuss features later today, but the feature relations are quite complicated. So there is significant dependency between the features, so various kinds of decomposition may be useful, but if you're not doing decomposition, you may want techniques that are able to use many features at the same time.